Yeah. I saw that yesterday. I was yeah, I gotta be like, I'm not gonna give you a I think you have to say like what I want to say that's just
you want a hint? Good morning.
Yeah.
Yeah. Can I call? All right. How's your day going? All right. All right. How many people can solve this? Like geometric substitution. So sorry, trig substitution. So cos x is derivative of sine x, and then it's just like 1 over a linear thing. So that's the log. Say it? That's just a coefficient. Who cares? Like you'll figure it out. Yeah. So okay. Anyways, unlike some other mean instructors, I only give one option in the multiple choice thing, so it's okay. Okay, all right. So I want to finish up graphs today, but I also want to make sure that I talk about lab 10, which is about vibe coding. So we'll start doing that first. I'll walk you. So we made it like yesterday. So I hope it works. It does require a bit of a setup. So basically, you can interact with LLMs like ChatGPT or Claude via the internet, of course, by just chatting to them. However, you can also interact with them programmatically using what's called an API. So that just means that you can send them stuff from your code and get a response from them into your code. So that is how ChatGPT works behind the scenes. So part of what we're trying to do in this assignment is to just get you to use this kind of API. And then another part of the assignment is just thinking more about how you would code efficiently with LLMs when they don't give you the answer straight away. And that's something that Andrej Karpathy, who actually was at U of T, he graduated in 2009. Now he's famous, so he invented the term vibe coding. So vibe meaning the atmosphere, a vague sense of what's going on. So vibe coding is just like telling the LLM vaguely what you want and then getting a response back from it. So, okay. So the first thing I want to show you is interacting with GPT via an API. So basically what you need, so basically the way it works is you have a library. So people ordinarily use OpenAI, and then you pay OpenAI, you give them your credit card, you get an API key, and that allows you to interact with OpenAI directly, not via the chat. And the way the payment works is, you send them the key every time you send a request, and they bill you for the usage. So we can't have everyone sign up for OpenAI. It's not that expensive actually, but they have to have a credit card. It's annoying. Anyway, so we have our own thing called actually. So Chris Peach from Stanford gave it to me. So it's called Not OpenAI. It works like OpenAI. Basically, I paid for an OpenAI account. We then generated keys for you guys. Everyone now has a key. There's instructions about how to get your keys. And you can interact with not OpenAI the way you could try to interact with OpenAI as well. So we're giving you a function that does it. So essentially so the syntax here doesn't matter. The syntax also changes all the time. So those things are, in flux. But basically what we have here is you are getting so you're saying, I want to use my client, which is not OpenAI with this particular key, and I want to get a response from it. And the way I would get a response is I plug the prompt in here. So this is the prompt over here, and this is the response string that I get. So the way I would use it is just say get response. And here, what I would do is I would just say, okay, I don't know, what is praxis? So something like that. And then you wait, and hopefully it'll. Okay. Yeah. So there's your answer. Okay. So basically, you just interact with it like this, and the advantage is you can do it just from Python. You can then, and that's what you will do, actually process the output further. Make sense? So this is someone's API key that I just grabbed. So we made a thing here where if you go here, you can get your API key by getting by inputting your email, and you'll get the API key. So especially during the lab, please be careful with it. So we are allowed as a class 3 requests per second or something like that. So please be gentle with it. Nothing I can do. You can sign up for OpenAI with your credit card, and then you won't be as limited, but it is what it is. So please don't keep requesting things in the loop or anything, and be a little bit patient with it. Okay, I paid $10 to OpenAI for all the keys to be able to get all the keys and stuff. So yeah. Anyway, okay. So questions so far about this framework? Like basically nothing. Like basically what we are doing here is we are, inputting a prompt and we're getting a string as a response. All right. So what we're doing in the lab is, so here you'll be just testing it. So we're going to try to write code that generates a Python function, and then we want to test the function automatically. The idea is that one way, and in fact, kind of the paid Claude, for example, does that. One way to generate code that actually works is to send the prompt, and along with the prompt to send test cases. And then what it would do is it would just generate some code, try to run the code, see if it passes the test cases. If it does, great. Maybe it'll generate more test cases. If not, maybe it'll try again. Okay, so your task here is to basically do that on your side, right? So you'll get some test cases, and you'll also check the result from the generated code with the test cases. So if you remember how that's done, so Emerson here basically kind of solved it for you. There's some more code that you need to write. So basically, if you have code, you can execute it with exec, at which point the function is defined. And then when it's defined, you can just run every test case and see whether it passes everything. Okay. So the idea here is you'll generate a simple function with GPT and then automatically send it to check results and see that it actually passes. In principle, you could have, if it's something complicated, you can have something like a loop where if it doesn't work, you maybe see, well, like try to automatically figure out why doesn't it work. One way to automatically figure it out is send the whole output to GPT again, see what it says. Or you just try generating a couple more times until it works. That's the usual strategy for students. That doesn't work that well. So yeah, okay, does that make sense? All right. So I also wanted to give an example of a situation where GPT-3 doesn't succeed. And so the latest version is whatever, 4.5. So 3.5 is pretty old. It's 2 years old, I believe, at this point. But nevertheless, even 4.5 on this kind of thing doesn't work that well. So it's not easy to find those examples. So that's the one that I came up with. So the idea here is you have this kind of string, maybe you like copy paste in a table. And what I had done here, so this is like the characters from Snow White, I guess. So what I had done here is there's some missing data, right? So there is some missing character names, and then there's some missing dates. And the way they're missing is the annoying way where there is a comma either way, whether there is missing data or not. So it's not like extremely difficult to figure out how to parse this out into kind of a table that makes sense. Just check whether the first thing is a date, and if it's not a date, if it's a string, then then the date is missing. Otherwise, if what comes after the date is a number, then the name of the character is missing, stuff like that, right? But that's not something that GPT 3.5, at least when I tried it this morning, could do automatically. So this is just to demonstrate that if you do that and you just say, well, like, I want to get the response like this, and just figure out Python code that reads the S correctly, and the S is just that string, what you'll find is that probably it doesn't work. So the next task is, well, suppose that, like, this is an extremely usual situation I encounter it all the time, right? So I have some kind of table from like a conference I'm running, or from like students or something, and they like copy and pasted it, and there was missing data and it's not formatted well. So an extremely usual situation. So try to figure out with chatgpt.com, please, not with my limited resources from not OpenAI. Figure out a way to nudge it towards actually getting the right solution. Once you figure that out, then you can try it with the framework that you develop. And then finally, we are not done with graphs. So what I'm asking you to do is generate some more data with the code from last week, and write a function by hand, please, that answers a question about the graph. Okay. All right. So that is lab 10. And we are back to talking about graphs. So, by the way, so just like to get an idea, so how many people code with ChatGPT or something like that? Okay, so about half. Yeah, I don't know what to tell you. So I think, like, obviously there's like I think on the one hand you should know how to use modern tools. On the other hand, yeah, like when you're practicing for the exam, probably like go easy on the ChatGPT. So yeah. Okay, all right. So where we stopped last time with graphs is we were writing DFS recursive, and it almost worked, except I forgot to advance her neighbor, which is why it was hanging. So this is posted. This was posted like 5 minutes after last lecture on Piazza in the comment at the top. So we are also, by the way, so the course notes are like basically up to date. So you can always go to the course notes. We are currently in the algorithm section. We are trying to keep them basically up to date. So there is going to be a text description of everything there as well. So, okay. So to remind you what's going on with DFS recursive. Go to the slides. So we are on the last slide of graphs. So the basic idea is just this, right? So we're saying in order to traverse the entire graph, well, traverse whatever node you start with, and then traverse the graph starting here and traverse the graph starting here. So using the neighbors, right? And then if you are traversing 6, you're going to say, well, traverse the neighbors, so traverse 5. And also this is waiting around. So eventually it'll also say traverse 2 and traverse 4 if those weren't visited yet. Okay. The way we're implementing it is we're saying, okay, so we need to keep track of which were visited and which were not. So we just create this array where initially nothing's visited. Then we start by visiting current I, and visiting means we mark it as visited and we also print it. And then we go through the linked list that's connected to current I. So this is current neighbor. We start with we start with the head of node number current I. And then for anything that's not visited, we just call DFS_rack on that. So there is a bit of an annoying thing where we call it with the name, right? So we call it with the name of the airport, but we need the index. So we go back and forth between what's the name. So the name is cur and the index is cur I. And this is why here we look up the actual name of the index. So that's the price that we pay in order to be able to refer to them by name as well. Does that make sense? So let's now let's now run depth first traversal and then DFS_rec. Let's actually do DFS_rec first. So we do DFS_rec from YVR. And this is what we get. So let's try to trace what's going on here. So we obviously start from YVR and we go to YYZ, right? So that's obviously going to happen. At this point, the question is, are we going to go to YUL or are we going to go to JFK? And this is actually predictable. So if you remember from last time, we were talking about, okay, like in the linked list, what is that going to look like? And the answer is it's going to look like this, just because this is the order in which we put in the edges. So what's connected to YYZ is this. It's like YUL, JFK, YVR nodes. So that's the linked list. The way the recursion works is we're going through this linked list and immediately we are at a node in the linked list, we call DFS on it. So that means that what's going to happen is we're going, so YYZ, the first thing is going to be YUL. So we just call DFS YUL, which is why YUL is what's visited immediately. Immediately, the thing that happens when you call this is the node gets visited, right? So then you are at YUL. If you're at YUL, well, you'll go to YXZ next. That's depth first. After that, the only other branch that's left is you go JFK LAX SFO. Is that making sense? So that's the order. So that was a question from before, like what's the order? So the order here is like this. An interesting thing is that if you call our original depth first traversal, it's going to be the other way. So here it goes, again, it's still depth first. So it's going to go YVR, YYZ, but then it's going to go JFK, LAX, SFO. And there is a reason for, and then it'll go along this branch. And there is a reason for that as well. So it's not magic. If you look at depth first traversal, what is the order in which the neighbors are visited? Well, what's happening is when we are visiting something, we are going through the linked list and we're adding every neighbor to the stack. And then the last neighbor that was added to the stack is the first neighbor that's going to get visited. Because that's how stacks work. Does that make sense to everyone? No? Yes? No? No. Who says no? Okay, some people. So if you remember, like what's going on here, big picture. So the big picture is we are visiting some node. When we're visiting some node, we're adding all of the neighbors to DS, in this case, the stack, right? So in what order are we adding the neighbors to the stack? Well, in the order that they're stored in the linked list. So if we're thinking about YYZ, the order in which they're going to be added is YUL and then JFK and then YVR, except it's been visited already, right? So once all the neighbors have been added to the stack, we pop the first neighbor in the stack and visit that neighbor. So if they were added in the order YUL JFK, the next thing that's going to get visited in the traversal is JFK, because JFK was the last thing that got added to the stack. The way we figure out what to visit next is we just look at what's at the top of the stack. Does that make sense? So if you really want to go in depth here, what's going on is the orders are not exactly the same, right? So here, when we're doing it recursively, we are saying definitely from YVR then to YYZ, and then we first go to YUL because YUL is at the head of the linked list in the list of neighbors. And when we're doing it using the stack, it's actually the other way, just because we first add YUL to the stack, and then we add JFK to the stack, and then we pop off JFK from the stack to visit it next. So this is actually kind of very implementation dependent, but at the same time, good to know exactly what's going on. So that is why. All right. Okay, questions about this? All right. So I am going to do the last set of slides about graphs. But first, I need to very briefly talk about the priority queue abstract data type. So we all hopefully at this point know about queues. So a priority queue is a queue where every element has a priority. So specifically with a min priority queue, what's happening is rather than retrieve the first element that was inputted or the last element that was inputted, we output the element with the smallest priority that there is. So I'm going to implement this in a non-efficient way. And then I'm just going to tell you how to use it in Python. I decided not to do the implementation of priority queues this year because I want to do like a few lectures on AI, or like the good implementation, I should say. I am still going to do the bad implementation. So here's how that's going to go. So basically the same thing as before. We'll say that we'll store everything. I'm not going to do this. This is the fancy one. So insert. So what I'm going to do is I'm just going to say, okay, so insert. And the way I'm going to do it is I am just going to append this tuple. And could do it this way, but I'm actually going to do the expensive extract instead. And here I'm just looking through all of them, and I'm looking for the lowest priority. and I'm extracting that. So pop is convenient because pop gets you the data, and it also removes this index from the queue. So I probably just want the data, so I'll just return like 0. Okay. Does this code make sense to people? So I can do it like this. And like you might imagine that you're using this to simulate like, let's say we have like a queue of students in office hours or something, right? And then the priority, the way we do it is lower gets extracted first. So maybe what would make sense for lower gets extracted first? So maybe we want to be fair, and we want to like get to people who asked fewer questions before. So this would be like the number of questions that got asked, right? We'll do like 1 with 5 or something. So something like that. And then when we do PQ extract min, that should return Alice, because Alice has the smallest priority, which means that that's what gets extracted first. And then if we do it again, that would be Bob. Make sense? So that's a priority queue. So where would you use it? So for example, it's used when simulating a hospital. You can actually imagine using it. So people actually do kind of optimization of kind of how do you allocate nurses and stuff. And in order to know how to allocate nurses, you might like to just simulate the hospital. And then you would have simulated patients arriving with different priorities, and in the emergency room, they do see people with the highest priority first. So you'd be able to figure out like what the load would be, stuff like that. People also use it in order to to simulate internet traffic. Again, kind of with internet traffic, some packets that are traveling on the internet have higher priority, you might imagine at least. And then you could figure out like the best algorithm for routers to decide kind of which packet to send at what point, stuff like that. So that's kind of the general use of it. We'll use it for graph algorithms, which is why I'm talking about it right now. So one thing to note here is that this implementation is efficient for inserting, but not efficient for extracting, right? So insert here is of 1, but extract min is of n, where n is the number of elements in the queue. And that is quite expensive. So there are efficient ways of doing it with O of log n extract and insert. So, okay. So that was a short detour into this, and now we'll use it. Okay, so I want to talk about a task. So let's say that you have a weighted, yes. Let's say that you have a weighted connected graph, something like this, and you want to find so people say shortest, but in this context, it's really the cheapest path, between, let's say, 1 and 4, right? So what we mean by path is a sequence of edges where the consecutive edges connect nodes that connect to each other, essentially, right? So a path would be like something like this, from 1 to 4, right? So you might imagine that what you want is the cheapest path from 1 to 4, and it would be probably something like that. So probably something like this, right? So okay, so where might you use it? Well, for example, if those are airports and the weights on the edges are prices to get from one airport to another, then this would be the problem of figuring out the best, cheapest flight plan, right? Does that make sense to people? Does that not make sense to people? Okay. So, all right. So so this is not going to be an easy algorithm. So the algorithm is actually like not amazingly bad, but the proof that it works is kind of bad, but it is what it is. So here's basically the inspiration for the approach. So if you're trying to find the shortest path, the cheapest path from A to H, and you have a bottleneck here, right? So you definitely need to go through E in order to get from A to H. Of course, you don't know this ahead of time when looking at the new graph, but here it's kind of obvious, right? You have to go through E. Then you can decompose the problem into what's the cheapest way of getting from A to E, and then what's the cheapest way to get from E to H, and that would be the total smallest cost, right? This is more inspiration than anything else, because in general, saying, oh, I know what the bottleneck is almost as hard as solving the original problem. And sometimes there is no bottleneck. Sometimes there are several good options, right? But that's the basic inspiration. And this is the actual algorithm. So the algorithm, like if you look at it like this, it's like nothing, not a lot of lines, but it's a little bit difficult. So it's called Dijkstra's algorithm, after the Dutch computer scientist Edgar Dijkstra. Fun guy. If you Google for his essays, he has like a lot of opinions about a lot of things. Or had, I guess he's died. Yeah. So here's what we do. So we basically say, okay, so we start with the source, aka source. We start with the source and we record the distance to the source is 0. So d of v, it's kind of like when we defined the cost array in dynamic programming. It's by definition the cost of the shortest path from source to v. And the cost of the shortest path from source to source is 0, because you're already there. So that is why we say d of source is 0. So what we're doing now is we keep going, and it turns out that there is every time one more node for which we can actually know what d of that node is. So specifically what we do is we say, look at everything that's already in S. So initially what's already in S is just source. And then find a new node such that du plus the edge from uv is minimized. And the claim is we can now compute dv. And this is not obvious at all, but what's true is that this d of v is correct, right? So this d of v would be the actual cost of the cheapest path from the source to v. And we keep doing it until we compute the cheapest path to everything. Yeah.
So what do gain represent here?
So e there is no e. So you mean u?
No, I like function definition.
Oh, this is just like the graph is the vertices and the edges. Yeah. Okay. So let's look at the picture. So here is what's going on with kind of in the middle of Dijkstra's algorithm. So we started with the source, and so the grayed area is the set of everything that we've already put into S. So remember, the set of everything that we've already put into S is all the nodes to which we know the cheapest path. Okay. And now we're saying I want to add another node that for which I did not already record the cheapest path to S. And the way I'm doing it is I'm saying, look at everything. So let's say that what we have is just two candidates. So we have Y and we have V that are not in the set S. I'm saying, look at everything where I can go from something that's already in S to something outside of S and find me the cheapest path. So that would be either S to U, U to V, or in this case, S to X, X to Y. Right? So find me the cheapest sum where I go from S somewhere inside gray plus one step outside the gray area S. Make sense? And the claim is if S to U plus UV is as small as possible, then it's definitely the case that the way to get to V that's the cheapest is S to U and then UV. So I'm not going to test you on the proof for why that is, because I don't know a question other than reproduce the proof, which would be silly. And then we'd have to read the proof, which would be terrible. But here is the proof of why that actually works. So again, what am I trying to prove? I'm trying to say, if I already know the distance to U and the distance to X, and X and U are the only ones along with S that were already visited, and I'm trying to find another node to which I definitely know the distance from S, meaning the cheapest path, then the node to which we have the cheapest path is a node such that S to U plus UV, or the other candidate is S to X plus XY, is as small as possible. And the argument goes by contradiction. So let's say that even though S to U plus UV is cheap, could there be a cheaper way to get to V from S? Well, in order to get from S to V, in order to get from S to V, what would you have to do? You would have to go from S somewhere else in gray, because if there were a direct cheap way from S to V, we would have already seen it, because we already added SU, so it must have been cheaper than the hypothetical SV, right? So it would have to be that we go from S somewhere else, let's say to X, and then we've already selected SU plus UV as the cheapest one, so there definitely is not anything cheap from SX directly X to V. That's excluded. So the only possibility is S to X, then X to some Y, and then Y to V. But S to X plus XY is already more expensive than S to U plus UV. So that doesn't work either. Does that make sense? Yeah.
How do you know it's already more expensive?
Well, because by assumption, I assumed that S to U plus UV is the cheapest that I see right now out of all the alternatives of jump from S somewhere and then jump outside of the gray area. So it's definitely smaller than S to X plus XY. Right? So the alternatives are I can go from S to V directly, actually, not the case, because then it would be cheaper than SU and it would already have been visited before you. So that's not that. Or I can go from S to some other X and then go from X to V directly, not the case, because by assumption, S to U plus UV is smaller. Or I can jump from X somewhere outside and then go to V. But that's definitely not cheaper because S to X plus XY is already more expensive than SU plus UV. Okay, there you are. You can just trust me, or you can ignore what I said for the last 3 minutes. The point is, it works. So you keep computing the source, and if you if you keep computing dv, and if you add the v's in this way, then what happens is you eventually get the shortest path, the cost of the shortest path to every node in the graph. Okay. Who's okay with this? Okay, I'm not asking who's not okay with it because. So, okay. So what's the complexity of that? That really depends on the implementation details. So what we are doing here, right, is we keep a set of visited nodes to which we already computed the distance. And then in the simplest implementation, so every time we add another vertex to S, the set of all the nodes to which we computed the distance, or like the shortest path. But every time we need to look through like n, and then through n-1 candidates, n-2 candidates, n-3 candidates. That's all v squared at the very least, where v is n, the number of nodes in the graph. Are people good with this? Who is not good with this? Okay, so it is possible, if you were to know how to implement a priority queue efficiently, it is possible to use a priority queue when you're adding the neighbors. So the basic idea here, and I'm not going to do it in detail, but just so you know that it's possible to do Dijkstra kind of reasonably fast. So the basic idea is we have a priority queue that stores the candidates to add. And every time we visit a node, we add its neighbors to the priority queue, with the priority being the tentative cost of getting to that neighbor. Does that kind of make sense? And then if you remember, for an efficient priority queue, it's logarithmic time, so to extract and to add, and then you just do it as many times as there are edges. So this is why it's like this. I'm not doing this analysis in detail. I think there are more interesting things to get to in this course, but it's also equally important to know that Dijkstra is actually pretty efficient if you think about it. But it's like 2 lectures to do this in detail. So yeah. All right. So so far, what we've been talking about is computing D of V, meaning computing the cost of the cheapest path from the source to the destination node, right? That doesn't give you the cheapest path, it just gives you the cost of the cheapest path. But it's pretty easy to adjust the algorithm in order to store the cheapest path as the actual path as well. So what you do is when you're saying, I know by the hand wavy proof that the cost of the cheapest path to V is the cost of the cheapest path to U plus the cost of the edge UV, well, what that implies is in order to get to V, you need to go from S to U and then from U to V. So you just record U as the node that comes before V in the cheapest path. So let's look at the picture again. So when I'm saying D of V is the cost of S to U plus the edge UV, what I'm saying is the cheapest path from S to V goes through U, right? That's what it's saying. So I'm recording the distance to V is distance to U plus the edge UV. And I can also make a note for the node V, the way to go to V is through U. Make sense? So I'll just record, the node previous to V is U. And then what I'll do with that is I'll just say, okay. So if we want to recover the path, we just start from the end, look at the previous node to the end node, look at the previous node to that, previous node to that, previous node to that, and that's going to be the cheapest path. Does that make sense? Yeah.
Is there a destination node specified?
No, so Dijkstra finds so you could, if you do, then you can just stop computing once you encounter the destination node and compute the distance to it. But this computes the cheapest path to everything.
Or like we go through everything.
No, so what this algorithm does is it computes D of V for every node V eventually. And if you also add the previous, it computes where to go, kind of how to get from S to any node. Yeah. Is that making sense? All right. Okay. All right. So that is Dijkstra. I am not going to torture you this year with the efficient implementation of Dijkstra. We'll do the A* algorithm next time, and then we're moving to neural networks. All right. I will see you. Bye.